So as promised, I'm going to talk about logistic regression. And to implement the logistic regression model for this project I'm working on, the Bird Song Classifier, I'm using Tensorflow to implement the logistic regression. This logistic regression is really simple. We don't necessarily have to use TensorFlow, but since I'm going to be using TensorFlow for implementing the V4 neural network and the CNN and the RNN, I figured I'll just use TensorFlow for the logistic regression as well. So as mentioned, you don't have to use TensorFlow. You can also use the scikit-learn or PyTorch. Yeah, so for this video, I'm gonna be using TensorFlow, and I just copied the notebook that I had for support vector machine, and because all the process of loading the features and labels are the same, the only thing different is the model. So in this notebook, I already loaded all the features. I'm just gonna go over them real quick. So first thing is, we need to import the TensorFlow. We're importing as a TF by convention. And then we're loading the features and labels from the pickle files. This is the same process as what we've done for this Pro Vector Machine and XGBoost video. So we first load the audio features and the non-audio features. And we confirm the labels are the same between no audio and non-audio features. And then we shuffle the data and we take a look at the shuffled data. And for both audio and non-audio and the training and validation. So this is the validation portion. And then we do the one-hot encoding for the continent. And then, so now we're at the logistic regression model portion. So I already remember for when we did the support vector machine and XGBoost, basically we concatenate all the features into different rows, different columns, I mean. For example, the training features, we have 8,000 rows, which is essentially 8,000 samples, and then 59 features. For example, MMCC would be the first 20 columns, and then the chroma would be the next 12, and so on and so forth. And everything added up is 59 columns. Basically, you can view this as. And the same for validation. We have around 4,000 validation samples, each with the 59 features. So to implement the logistic regression model, I am going to actually create a function here. And I'm going to create this function and I'm going to call it as the build model. And I'm going to give it two parameters. One is the feature parameter, which is I will be using the feature parameter to tell the model the shape of my feature. And then I'm also going to passing the learning rate as one of the parameters. So the learning rate, I am going to set the default to be 0.005. And this is just arbitrary. You can put it as whatever you want. And then the first thing I'm going to do is I'm going to clear the back session for TensorFlow. So I do this so that each time when I call the build model function, it clears the back session so that it clears out all the weights, just in case the model is, continue to learn from the previous model. Okay. Here's the backend clear session. So I first clear the session, and then I instantiate the model by calling the TensorFlow sequential. So here I'm using the Keras sequential model. There's also the Keras functional API, but here I'm going to just use the sequential. And the only difference between logistic regression and, for example, V4 neural network is for logistic regression, there's no hidden layer. So I'm going to first set my input layer. Okay, so to set my input layer, I'm going to do model.add, and then I'm going to call the TensorFlow input layer. So for the input layer, it's going to ask me for the shape that I should specify, which is the input shape. So here I'm going to use the parameter input features to get the shape. And this is going to be the number of features, which is shape 1. So for example, shape 0 is going to be the number of rows, and then shape 1 is going to be the number of features. Okay, and then I need to give it a name. This one is not strictly necessary, but it's just good practice to so that we know which layer it is. So here we have the input layer. Okay, and then I'm going to set the output layer. Again, we have no hidden layer here because it's just a logistic regression. So we only have it's basically a shallow neural network, and we don't have any hidden layers. So I'm just gonna add the output layer. The layers, dense. So the output layer is gonna be a dense layer, and the unit is is 3 units because we have 3 classes. Remember, we have the 3 different species: bar swall, kamsan, ewag wang. In the case if we only have 2, so in the case if we only have 2 species, then our output unit is gonna be wang because it's gonna be binary. Okay, and then my activation function is gonna be softmax. Again, I'm using softmax because we have 3 or more than 2 output classes. If we only have 2 output classes, then my activation function should be sigmoid. And again, I'm going to give a name, which is going to be the output. And now I have the architecture of the model ready. I am going to compile the model. So to compile the model, I can use model.compile. And I need to specify the loss function. So for the loss function, I'm going to use this sparse categorical cross entropy. Sparse categorical cross entropy. Okay. And I also need to specify the optimizer. So for the optimizer, I'm going to use Atom. You can also use another optimizer that commonly used is SGD, which stands for stochastic gradient descent. Atom is just is a little bit nowadays more people use Atom than SGD, and because it has the slightly better performance. So I'm just gonna use Atom here. Optimizers.atom. And to also for the Atom, I need to specify the learning rate. So the learning rate is gonna equal learning rate, which is the parameter that we're going to be passing in, so that we can change the learning rate if needed. And I'm also going to specify the metrics. And for this one, I'm just gonna use accuracy. There are many different metrics that we can use, such as recall, precision, and F1 score, and many others. But for simplicity's sake, I'm just gonna use accuracy. Also, I'm using accuracy because my training data has the no class imbalance issue. So I think accuracy is okay for our case. And then I'm going to return the model. So this is my my build model function. And when I am ready to build the model, I will pass in the input features and the learning rate. And the function is going to build my model and then return my model. And to fit the model, with the training data, I can just do model.fit. And then to predict using this model, I can just do model.predict, and I will show you shortly. Okay. And the next thing I want to do is I actually want to define a visualization function so that I can visualize the learning. And this will become apparent in a bit on why I want to visualize the learning. So I'm just gonna write out this function. Basically, it's the function is called visualize, and I'm going to pass in the model history as the parameter. Okay. as the loss. So I want to visualize the loss, and I want to visualize the accuracy. Okay, so I'm gonna have two subplots. So I'm gonna put fig and axes subplots, and I need to tell it how many rows, and I think I'm just gonna put one row, and then but I'm gonna have two columns equals to 2, and I also want to specify the size. And for the size, I think I'm gonna do 15.5. We can always change this if the size turns out to be not very nice. Okay, so for the visualized loss, I'm gonna put in the first axis 0.plot, and I'm going to plot the model history. Okay, and I'm just gonna tell it what color I want. So this is gonna be the training loss. I'm just picking arbitrary color, which is purple, and then I'm gonna label it to be losses. And then I also want to plot the validation loss, and it's gonna be called val loss. And then the color I'm gonna use orange, and label I'm gonna put validation loss. Actually, I'm gonna specify this to be training loss, and the validation is gonna be validation loss. And then for best practice, I'm going to set the X label, Y label, and give it a title. So the X label is gonna be the number of epoch. And the Y label is gonna be loss. And the title is gonna be, let's say, loss progression. And I also wanted to show the legend, which are the labels here. Okay, and then similar thing for the accuracy. So I'm just gonna copy and paste this whole thing, but changing the axis to 1, since it's gonna be the second subplot. And what happened here? Okay, and I just need to change the history to accuracy instead of loss. And again, this is gonna be validation accuracy. And I want to change my label to show accuracy. Okay, this should be it. And then at the end, I want to show the plot. Okay. Okay, this should be it. Oh, I want to also change this to be accuracy. I cannot spell accuracy. Accuracy. Okay. So now my functions are ready. Remember to build a model, we need to use the build model function. So this is, where is it? Okay, so I want to first try using all the features. And let's take a look at the shape and the validation and the shape. This should be familiar to you. This is the same process we did for the earlier videos. Okay, and to fit the model with the training data, I'm going to first instantiate the model by calling the build model function. And remember, the build model function takes in 2 parameters. First is the input features, and the second is the learning rate. So for the input features, it's gonna be our training features. And the learning rate, I'm just gonna keep it the same as 5.005. Okay, and then the next thing we want to do is we want to use call model.fit, which is here. So I'm gonna use model.fit, and what do I need to pass in? So you can read the documentation on the TensorFlow website, but but essentially I need to pass in the X. So the X, which is the features, is gonna be my training features. And my Y is gonna be the labels, which is gonna be audio, EF, label, okay? And remember our audio data frame and non-audio data frame has the same label, so it doesn't really matter whether you use the audio or the non-audio. I'm just using the audio here. And then we also need to specify the number of epoch. For this one, let's just do 300 epochs. And then we also want to specify the validation data. And so for validation data, we have the validation features. And we also need to tell it the label, which is gonna be from the validation sub-dictionary, okay? And then we also want to, let's not forget the comma here, and we also need to specify the batch size. I'm just gonna do 32, and I'm gonna do verbose equal to 0. So verbose equal to 0 means I don't want to see the output from each epoch, okay? We can also set the verbose equal to 1. Actually, let's set verbose equal to 1 so that we can see the training progression. Okay, once we feed the model, I can then visualize by calling the visualize function. And I need to save this model fit. So the model fit is going to return the history, and I'm going to call the visualize function to visualize the history. Okay, I'm gonna run this code and expected. Okay, something happened. Oh, the model. Oh, because I misspelled learning rate. So you can see here, since we set verbose equal to 1, it's showing us the progression from each epoch. We have 300 epochs, so this is gonna take a minute. But let's just take a look at the first epoch. So the first epoch took around 6 milliseconds per step, and the entire epoch took around 4 seconds. And this is gonna keep showing me more and more. Okay, and then our beginning loss is 0.99. Accuracy, you can see here, this is the training accuracy is only 51%. And then validation loss is 0.97. And then the validation accuracy is around 52%. So as you can see here, as each epoch, as the model trains, each epoch, the training accuracy and validation accuracy continue to increase. This is a very good sign because that shows that the model is continue to learn features from the training data and showing the accuracy from the validation data. Okay, so here I am actually going to pause the video real quick while this trains. This is gonna take a few minutes. All right, so the model has finished training and it took around 3 minutes. So we can see here for the last epoch, our training accuracy is 73% and our validation accuracy is 64%. And using the visualization function that I defined earlier, we can take a look at the loss progression and accuracy progression throughout the training process. So the x-axis is the epoch and the y-axis is loss or accuracy. I realized I didn't change this to accuracy, so I am going to have to change this here and rerun this in a bit. I'm just going to leave this for now because this is going to take some time to run. But for the sake of this video, I'm just going to go over these plots. Essentially, the first one is the loss progression, and each epoch is the model is running through all the training samples during each epoch. So here the model has seen all the data, all the samples for 300 times essentially, because we ran for 300 epoch. And you can see here the loss continued to decrease for the training and the validation. But one thing that I want to point out is you can see here the curves are really have a lot of zigzag, especially prominent for the validation. That is suggests to me that the model is struggling to capture some information from the training samples. So essentially the model is not, there are some features within the validation set that the model cannot really quite grasp by looking at the training data alone. So one thing that we could try is k-fold cross-validation, or we can try using a more complicated architecture to see if the model is able to learn more complicated features from the training data that could generalize better to the validation data. But for the sake of the logistic regression, I'm just going to leave them as is. And the same thing for the accuracy progression. You can see at least up until around 100 epoch, the model is steadily learning. But then after 100 epoch, the model is kind of hitting a bottleneck and is not really making too much progress anymore. Okay, and one thing to note is, remember, for our random forest and XGBoost and support vector machine, our validation accuracy was around 74%, 70-ish%. But see here, after our last epoch, our validation accuracy is only 64%. So the model is certainly not doing better than random forest or XGBoost or support vector machine. And this is kind of expected because since we're using just a shallow neural network logistic regression, this is assuming that's making the assumption that the data is linearly separable. But I think we can be almost certain that our data is not linearly separable. So we'll probably need a more sophisticated, more complex architecture in order to grasp more of the features, the nonlinear features from our training data in order to generalize better to the validation data. Okay, so the next thing I'm going to do is I'm going to use the model to predict, to essentially put the accuracy into the dictionary, so that we can take a look at the total training and the validation results later, similar to what we have done for the other models, because we're going to experiment with the various different combinations of features. And we will also evaluate the results by looking at the classification report and looking at the confusion matrix. So I'm going to first calculate the accuracy. Basically, it will be the last epoch accuracy, but we can just use model.predict to get the training predicted label. So here I'm gonna call it train y hat, and I'm gonna call model.predict by passing in the training features. So what this is gonna give us, and we can take a look real quick actually. So you can see here, the train y hat is giving us some numbers. And if we look at the shape, we should expect around 8,000. So this is the number of samples. And we have essentially 8,000 rows and 3 columns. So we can visualize these as columns. And what does the 3 column mean? So essentially the model is saying, okay, we have 3 classes, and for each class, for the first sample that I'm seeing, this is the probability that this sample belongs to the first class. the second class, and the third class. Okay, so these are all probabilities because I'm using softmax as our output activation function. It's going to give me the probability, and the probability of all three classes should add up to 1. And to get the actual output of what the model thinks the class the sample should belong to, I'm just gonna use argmax to get the class with the highest probability. Okay. I'm going to call this y hat result. And I'm gonna use NumPy's argmax. And I'll specify the axes. Okay. So now we can take a look at the train y hat result. And I misspelled axes. Okay, so if we look at the train y hat result, remember earlier for our train y hat, our shape was A2 around 8,000 rows with the 3 columns. But for training y hat result, now the shape should be just A236 rows, and each row will just only have 1 column. So here the 1 column is omitted. This is just by convention, but there's a 1 column here. And you can see here, so now our original 8,000 row by 3 column is now 8,000 row by 1 column. And each of these corresponds to 1 sample, which is the output from the model that the model predicts the the sample should belong to which class. Okay, so we can also take a look at our original train y. Our original train y is actually the label here. So just taking a look at the first 3 samples and the last 3 samples, for example, right? So the first sample, the actual label is 1, and the model predicted to be 1. So the model was successfully predicting the correct label. For the same for the second sample, but then for the third sample, the true underlying label is label 1, but the model predicted to be label 2. Similarly, for the second to the last sample, the true label is 0, but the model thinks predicted the sample to be labeled 2. So this is just an interpretation of how to interpret the train y hat and train y result. I'm going to delete these. Okay, and to get the actual probability to be not the probability, to get the accuracy to be stored in the train y results all features dictionary, I am going to use the model.evaluate function. So what the model.evaluate function is going to take in is the original training label, the true underlying label, and the predicted label, and it's gonna calculate the accuracy and put it into the dictionary here. Okay. So the y hat result is being calculated within the evaluate function. I'm just putting the y hat and y hat result here for future use. Okay. And let's see. And I want to do the same thing for the validation. Okay, let's run both cells. And we can see here, the model is evaluating the training sample, and the final accuracy is 0.73. And I just realized that I should have put in the index here to index the second last, which is the accuracy. Otherwise, it's actually putting the both loss and accuracy into my dictionary, and we can actually take a look. See, we have both the loss and the accuracy, but I really just want the accuracy. So I'm actually going to change this to by indexing -1, which is the last sample, last element in the result, which is the accuracy. Okay, I will run this again, same as this. Okay, and just to take a look whether our accuracy was saved successfully, we can take a look. And indeed, we have the all features, and this is the accuracy, right, from this 0.7325. Okay. And to evaluate the results, I am going to take a look at the classification report. And we already calculated the train Y results here, so over here on top, so I'm going to delete this, and we can just directly take a look at the classification report, the same as the validation. Okay. So again, the classification report is going to show the overall accuracy, which is 73 and 64% for training and validation. And then we can also take a look at the precision, recall, and F1 score for each of the classes. And the same thing, we can take a look at the confusion matrix. So the confusion matrix paints, like a picture for us on which label the model had did better and which label the model struggled a bit. Okay, so this is the training, and then this is the validation. So for example, in training, we can see that when the true label is Bourgeois, the model was able to get the correct label 1800 out of around 3000 at 3000. We have around 3000 Bourgeois. And, since we have total samples of around 8,000, each one is around a little bit less than 3,000. So the model was able to get Bourgeois more than 60% of the time correct. And similarly for CompScience and EWAG1. But then if we look at the validation, we can see that, for example, for Bourgeois, the correct label is here, all these added up together, but the model was only able to get around 930 instances correct, while the model seems like, it kept confusing Bourgeois and EWAG1 when the true label was Bourgeois. The model did really well with EWAG1 here. You can see majority of the correct label for EWAG1 was correctly predicted to be EWAG1. Okay. So that's it for the logistic regression. And I'm going to run the same model for the various different combinations of features using 5-second and 8-second framed audios with augmentation and without augmentation. And I will also do some hypertuning of the model. So hypertuning involves like changing the learning rate, changing the number of epochs, changing the batch size. And also we could change the optimizer, but yeah, I'm not going to show the details of my hypertuning and the results from all the other models in this video. You can read about it more on my website. And next, I will be talking about feed-forward neural network. It will be very similar to this model. The only difference is I will be adding hidden layers here. So please stay tuned, and I hope I will see you in the future videos as well. Thank you.